Hey there and welcome to another LeetCode problem. So today we're going to be doing problem number 37, Sudoku Solver. It's a pretty straightforward problem. The algorithm isn't too hard to figure out. It more tests you on, can you write it correctly, can you not have bugs, things like that. And so let's read the problem. Write a program to solve a Sudoku puzzle by filling the empty cells. A Sudoku solution must satisfy all the following rules. Each of the digits must occur exactly once in a row, once in a column, and once in a 3x3 box. And the character dot indicates, or period, indicates empty cells. So we're given this board of rows and columns, and what we need to do is we need to try to get a valid solution. Well, so remember, what are the rules for a Sudoku board, right? So rule number 1 is can't have, let's just make this bigger. Okay, repeating numbers in a row. Can't have repeating numbers in a column. And then can't have repeating numbers in a box. Okay, so how can we test for these things, right? What would be the easiest thing? Well, what's a really good data structure for repeating numbers? Just to see if, like, do we have it already? Well, it's going to be a set, right? A set is very useful for repeating numbers because we can have some numbers in here, and then we can quickly check, is a number in there? So if we use a set, well, we need to have these rows, these columns, and these boxes. So what we're actually going to do is we're going to have a dictionary for the row, the column, and the box. So the key will be the row or the column or whatever. So it'll be dictionary of rows, dictionary of columns, dictionary of boxes. And then it's going to have a set in it. And then we can easily, in big O one time, add or remove a number and check if it's in there. So the real trick with this problem is, how do we, for these boxes, this is pretty much honestly the only too difficult trick that you have to figure out is, so the rows and the columns are pretty straightforward because there's an index, but how do we get a dictionary of boxes, right? Like, let's say we have these 9 boxes. Well, how do we have a dictionary of that? And how do we, I mean, obviously we can just label them like this, right? But then if we have some index, like let's say we have something here, how do we know that's in box 1? Or how do we know this is in box 2, and so on? And so that's going to be the thing that is a little bit kind of tricky that you can do. And so actually what you could do for these boxes is you can take the row and you can take the column. And as you can see, so these rows go 0 to 8 and these columns go 0 to 8. So actually what you can do is we can just take a row and then we can actually divide it. So if we just take the row divided by 3 and the column divided by 3, well, let's see what that would look like. So if we're in, let's say, row 1, column 1, right? What would that look like? Well, row divided by 3, and remember this is the integer divide, so it's going to round down. Row divided by 3 would be 0, column would be 0. So anything in row 0, 1, 2 would be in 0, 0, and so on. So this would be, now once you can see this, you can figure out, okay, well, now this is 0, 0. And you know that right away, right? So we can have a tuple as a key, where we just have this row divided by 3 and this column divided by 3. Now let's say we're here, so let's say we're in some column 1, row maybe 4, right? So this would be 1, 0, and so now you get the picture, right? So 2, 0, then this would be, all these rows would be, let's see actually. So this row would be 4, I believe, right? So, or it would be 3, 4, and so on, and the column would be 0. So this would be, actually, so these should be reversed. So because this row shouldn't be 4, this should be row 1 still or something, column 4. So actually it would be like, yeah, let me get rid of these. Okay, so it should be more like this. It should be 0, 1, 0, 2, right? Because the rows stay the same, the columns are moving up. And now here is 1, 0, right? 2, 0. And then this final one would be 2, 2. And so that's how we can quickly get the box that we need to be in, is we can just do this row mod 3, or row divided by 3 and column divided by 3, and we can have a tuple, and we can have the key in the dictionary for the boxes. So now that we know that, what else do we need to do? Well, we need to also put in these starting values, right? So we need to take the board, we need to go through the board, and then we need to put in the starting values for the dictionary. Now, do we need to do that, or can we do that as we are going as well? That's the other question, right? And the answer is, I think we can do it as we're going. Yeah, definitely. So I think we can do it as we're going. So we can just have a backtrack method, right? So we'll just call it backtrack. And we're going to be going, whoops, a little early in the day. So we're going to be going through index I and j, let's say, which is the row and the column, and we're just going to be checking, okay, is it a value that we already have? If it is, just put it in. And if it's not a value, then what do we have to do, right? So let's say we put in this 5, we put in this 3. Now we're at this dot. Well, what do we have to do? So actually, this is a common backtracking method. And the nice thing, well, once again, the easy really way to tell that this backtracking is good here, because if we look at the length, I said this in a lot of other videos, look at the constraints. The constraints are really small. So if it's only 9 by 9, we can definitely do backtracking, and it's not going to be too expensive. It's not a big deal, right? If this was like 9 times, or this was like 10 to the 9th, and this was 10 to the 9th or something, well, now it's going to get really expensive. So the way to see these backtracking things is, like I said, look at the constraints, and if they're really small, then backtracking is good. Because backtracking isn't the most efficient method. We're pretty much brute forcing every single solution, and then trying to see if we came up with something. Okay, and so that's what we'd have to do. We'd have to go through these numbers. We'd have to say, okay, are they a number or are they a dot? And if they're a dot, let's try every single number. And so this says actually we want to, I believe we want to solve this in place. So we're just putting in a board, and we shouldn't have an output, I think. But I'll check that later. And so that's what we're going to be doing. We're going to be going through numbers one by one, right? Row by row by row by row by row. And then anytime we hit the end of the row, then our index is going to be the next one. And what's our base case? So our base case is actually when we reach the end of the board, right? So if we have this board, just say this is the board. When we reach the next row that's out of bounds, that means we completed the board successfully. And at any time we're going to put in a number, we're going to say, well, for our dictionaries of row, column, box, does it satisfy it? And if it doesn't, that means we have some duplicates, so it's not a valid solution. So we know we have a valid solution when we get out of bounds. We're just going to go row by row by row by row. And when we get out of bounds, we have a valid solution. And then we can either return true or whatever they want, or return the actual matrix. I'm going to look at the exact constraints. So hopefully that's pretty straightforward. It is a hard problem, but it's not too bad as long as you don't make too many mistakes in coding. The actual algorithm is pretty straightforward, how to solve Sudoku. Okay, so let's take a look at the... Yeah, so we're returning none, and I think we are modifying in place. Yeah, input, output. So then we don't really need to, so we are going to modify, and then what we're going to do is, by the way, as soon as we have a valid solution, we can just return true, right? Actually, do we even need to return anything? Yeah, so we want to return true if we have a valid solution, and then as soon as we have a valid solution, we can just recurse out because we know we have something good. But let's say we tried every number and it didn't work, then we can return false. Okay, so let's do that. So remember, we're going to have a rows dictionary, and let's just say this is default dict. And remember, we're going to have so it's going to be a dictionary of sets, right? Because that's going to be the fastest way to see if a number is in somewhere. Technically, because these numbers are only 1 through 9, you can just have a list and you can traverse the list, but we're going to do it this way. So columns, set, and then I'm going to call these 1 through 9 things here, I'm going to call these boxes. Okay. So okay. And so let's actually think one other thing. So if we are putting in these numbers as we go, is that going to make our problem slower. So actually, I do think we don't want to put in these numbers as we go. We want to put in the numbers that we have first, because, for example, I think that'll make our algorithm a little bit faster. Because, for example, let's say we just have, so this is just 1 9 thing square. So let's say we have like something like this. And we have some numbers in here, right? So let's say we just have like 1975 for this example. And we are here and we say, okay, we need to try every number. Well, now when we try 1, it's going to fail. Where if we didn't have these numbers and if we waited to put them in later, we'd traverse all the way down here before failing. Or sorry, no, we would traverse even farther, right? Like we would try this 1 here. Actually, no, we would traverse here before failing, and then it would have to go back and try another number. So we are actually going to populate this these with the numbers that we have for now. And then as far as rows and columns, so I'm just going to make those as well. They're going to be the same value, but okay. And so now we're going to iterate through this board and put in the numbers that we already have. So technically you can just use only a rows value because they're equal, but I'm used to this format. So okay, and now we have to check if board row column. So it says the dot is the non-empty, right? So we're going to do this. And I think what we want to do is, I think I'm going to store numbers probably, as opposed to, I'm trying to think if there's merit to having one or the other. I don't think it matters actually. I guess we can store strings. It's fine. Or actually, no, let's store numbers. Let's store numbers. Okay, so if board is not equal to this, that means we have a valid something to store. So then we need to do that. So rows row dot add. Oh, and by the way, so instead of this border, let's just do this. There we go. Okay, and then let's also do this. Just to make it. There we go. Column and temp. And remember, in our boxes, what we were going to do is we are going to take the row mod 3, or integer divided by 3, column integer divided by 3 dot add temp. Okay, so let's just actually print these just to see kind of what's going on here, just to make sure we did all that right. Because this does get a little annoying to debug for sure if you screw something up. And this is pretty much the reason that it's the hard problem, not because it's super hard to code. So let's take a look. So row 0, we have 357, which is right. Row 1, so that seems right. Now let's take a look at the columns. So column 0, we have 4, 5, 6, 7, 8. Seems right to me. 1, 3, 9, 6, 4, 1, 2, 6, 8, 7, 9. Yeah, I think that looks good. Okay. Yeah. And then let's check our boxes. So box 0 is going to have does that look good? This third one. So 0 has 3, 5, 7, only 1. It's interesting that this last thing has keys 1 through 8. So why is that? This should be a tuple. That should be a oh, right. Okay, it's because I'm an idiot. Okay. Okay, so 0, 0. There we go. So now it's good. So, yep, looks good. Okay. So now what we need to do is we need to write a backtracking algorithm, and then what we're going to do is we're going to actually iterate through every single number, and then if it's a number we already have in there, we can just go forward, right? Yeah, so let's do that. So def backtrack, row, column. Okay, and so remember our base case? Our base case is when we are actually, just minimize that. Our base case is actually when we are out of bounds, right? So if row equals square equals to rows, this is where we return true. That's our out of bounds case. Okay, now we have to check our current index, and then we have to see if we have to backtrack, right? So there's going to be two cases. If we so let's handle the case where we have just a normal number first. So let's do that. Yeah. So if board row column does not equal dot, that means that we already have something in there. All we have to do is go forward. And so the code to go forward, we could make a helper function for that. Do we want to do that? Sure. So let's make a helper function to go to the next grid. So it's going to take let's just call this a next place or something. Row column. So this is pretty straightforward. This is just if column equals columns minus 1. That means we go to the next row. So here would just be return row plus 1, 0, right? So if we're at the last column, then the next place we go is to the next row and down 1. So that's pretty straightforward. Then else return, then we can just add 1 to the row. Okay. So that's so here we're just going to go to, let's just call this new row maybe. Yeah. Equals next place row column. And then we just go there and then we are done. So that's all we're going to do. So we're going to go return whatever the next thing is. So backtrack and row and column. Okay. By the way, we could do this regardless, so let's just write that up here. Then this is the next column we're going to be going to. Okay. So now what we need to do is we need to handle our actual backtracking case. And so our backtracking case, well, what are we doing? So the way for normal backtracking is we're trying every single number 1 through 9. And the way to try that, right? So let's say this is this is some box we're in. So let's say this is row 0, column 0. And we just try to put in a 1. Now, when we put in a 1, what does that mean? We're not actually putting the 1 into the grid. But instead, what we are doing, actually, no, we are going to be putting the 1 into the grid. We are going to be putting the 1 into the grid. But what we also need to do is we need to put it into the rows and the columns and the boxes to make sure that when we check some stuff later on, right? Like when we try to put in something here and we try to put in a 1, well, we can't do that because it's in our rows. Where if we didn't do that, that would be an error. So that's how this backtracking works, is we need to put it into all our 3 dictionaries and then make sure we don't have any duplicates in the future. Okay, so let's do that. So for I in range, this is going to be rows technically, right? So we're going to put in, actually, this is going to be like this, because we're putting in, yeah, we're going to be putting in 1 through 9, right? We're not going to be putting in 0. So, okay. So then we need to, what are we actually doing? So we're putting it in the board. So okay, equals, and this is going to be the number, right? So this is just I. But remember, we need to put in as a string. So now we need to put this number into all of our dictionaries. So rows Yeah, we need to put it in. Oh, sorry, actually, by the way, before we even put it in, what we need to do is we only put it in if it's not in there already. So if it's, like, let's say we are here, and we don't need to try to put in a 3 because there's already a 3. So we have to check, first of all, is it in any of our dictionaries? And if it's not, then we're good. So if I not in rows row, and, right, not in columns column, and I not in boxes, and then this would be this. Right? So then we put it in. So we're doing all this code here. Okay, so stri, now we add it in. So rows, row, dot add I. Okay. Now columns, column. Oh, and it shouldn't be equal, it should be this. Now boxes. Okay, so now we add it in. Now we need to actually call backtrack, right? So, and we need to pass that next row and the next column. Okay. Now, what we need to do after that is we need to, so after we're done backtracking, we need to get rid of everything we did, right? So we need to remove from all these, and then we need to make this. So technically, we don't need to make this thing back into a dot. Actually, let's do that. It's only one line of code. It's not a big deal. So let's just take all this, and let's. So remember, this is just going to be back to a dot. We can technically do that at the end, but it's not going to matter. Now we have to remove. Oh, so we do have to do one more thing. So here, if this is true, so remember, if our base case returned true, all we need to do is recurse all the way back and just return. So if this is true, then we can just return right here. Otherwise, then we have to do all these removals. And then alternatively, I think actually if you want cleaner code, what you could probably, I'm not going to do that in this, but what you could do is you can have, if any one of these is a not, then put in a continue, otherwise do this, and then the whole loop isn't in an if statement. So that would be cleaner code if you wanted to do that. Okay, anyway, so now that we tried every single number, now remember for our last part, we just need to return here, right? So we need to return false because we tried every number, it didn't work. Now we simply call backtrack on 0, 0. And if there is a valid output, it should put everything in for us. So let's try that. And row and column. Oh, is there a space or something? Yeah. Okay, let's see what we got here. Interesting. So right now, it looks like we never find a valid case, I think. Yes. Yeah, so we never found a valid case in this case. So let's go through this real quick. If column equals columns minus 1, return row plus 1. So that makes sense. We go to a new row. Okay. Else return. Ooh, that's a problem. So we aren't going correctly. So otherwise, this needs to be row. And if column isn't the last column, then we just increment the column. So let's see if that fixed it. Okay, cool. It did. So let's try to submit. Cool. Okay. So let's discuss the time and space complexity. And I think for this problem, if you did a brute force solution, you would try 1 through 9 in every single cell. And then there's 81 cells, and all these states aren't like they're all different, so they all affect each other. If you have some number in one, then it affects the others. And so I think that would be for brute force. I think it would be of something like this, n to the n squared, because you have n different solutions and then there's n squared locations. So I think that's what that would look like. But for backtracking instead, for every row we have n factorial, because like if imagine everything's empty, so here we can put in 9 numbers, here we can put in 8, 7, 6, 5, and so on. So it'd be 9 times 8 times 7 times 6 and so on. And then now that's a row, and then we only have 9 rows, so that would be like this. So instead of n to the n squared, it would be this. And for space is pretty more straightforward. By the way, yeah, someone can correct me if I'm wrong for time, but I'm pretty sure that's right. For space, it would be n squared, because for every single one of these rows, column, boxes, we are storing every single cell, so that's just n squared, and that's all the space we have. Okay, so I would encourage you to try this problem. It's definitely a good one to try in backtracking. It's pretty vanilla backtracking. There's nothing fancy. It's just a decent amount of code, and you can make a lot of bugs. So I think this is a good one to start. And yeah, if you like this problem, please like and subscribe, and I'll see you in the next one.